Welcome to another cosmology talk. This week we have Natalia Porqueres, who is a postdoc at Imperial College. She had a recent paper on using forward modeling to learn about cosmology. Personally, I love forward modeling. It's one of my favorite things. And if I was to answer the question I always ask at the end of these talks of something you're not working on that you think is really interesting, it would be forward modeling. Because I got into cosmology because I was interested in the most fundamental stuff. And so while it's interesting to do weak lensing modeling and modeling of quasars and all these sorts of things, which I guess Natalia would probably call sort of summary statistics, bispectra, all of these sorts of things that are trying to get at the non-linear aspects. Ultimately, what I care about is what the early universe looked like. And so when you're sort of sitting together trying to work out what you should be doing to learn about that, ultimately it's just put all of it into a black box sort of and simulate it forward and say, this is what my observations are like at the end. And therefore my initial conditions had a certain shape. So she'll go presumably into a lot more detail than that, but that's why I like forward modeling. And I think this is one of the first forward modeling papers that has come out since I started this channel. So I thought I'd get someone on to talk about that sort of stuff. So yeah, this is specifically in the context of Lyman-alpha and quasars. Thanks, Natalia, for joining us. Do you want to have a quick intro into what it is that you do in the paper?
Yeah, sure. So first of all, thanks for having me. So this paper and in general my work is based on forward modeling techniques, as you said. And in this case, we are interested in inferring the dark matter distribution from the Lyman-alpha forest. So in this kind of forward modeling techniques, what we do is we start with the initial conditions of the universe and we evolve this to the observables that then we can compare directly with the data, with the real observations. But to do this, to go from the initial conditions to the observables, we need a description of the dark matter dynamics. So initially, we developed this method using Lagrangian perturbation theory to describe the dark matter dynamics, but this doesn't provide a good description of the density field inside the voids in the low density regimes. Mm-hmm. And what we have done in this paper is to improve our method by introducing a field-based approach to describe the dark matter dynamics that is more accurate in the description of the voids and the underdensity.
If someone's remembering this talk a couple of months from now, or remembering your paper, what are the two simple things? If there's nothing else that they remember, what are those two things you want them to be remembering?
Mm-hmm. So first of all, maybe a simple thing is that it is possible to infer three-dimensional information from the Lyman-alpha forest. So this data is limited to one-dimensional spectra, but with this kind of forward modeling techniques, we can interpolate the information between different lines of sight and recover all this filamentary structure of the cosmic web. Mm-hmm. And second, the second message, maybe more directly related to this paper, is that a field-based approach to describe the dark matter dynamics has some advantages over the more standard particle-based approach. Mm-hmm. Probably the most important advantage is that it provides a smoother and more physical description of the densities inside the voids, but also in a more technical side, it helps to speed up the algorithms and make them faster. So if you are trying to analyze data that requires a good description of the underdensities, this kind of field-based approach can be useful for your analysis.
Cool. And yeah, why did you do this? And I guess the sort of broad picture and small picture, why forward modeling, but then also why specifically now is it quasars and Lyman-alpha that are the thing that is being applied to?
Yes. Yeah, so as you know, many of the analysis of the large-scale structure are currently based on galaxy observations. So some of them are looking at galaxy clustering, some of them are looking at lensing. Mm-hmm. But we wanted to look at the Lyman-alpha in this case. And the reason for this is that the Lyman-alpha can provide complementary information to the galaxies. So mm-hmm. First of all, this data has a very high resolution. It has a resolution of 1 megaparsec along the line of sight. And this is higher than what can be achieved with galaxy sampling rates, especially if you're interested in the high redshift universe. Mm-hmm. And second, the Lyman-alpha forest is sensitive to the low density regimes of the universe. So the Lyman-alpha forest is a set of absorption lines in the quasar spectra, and these absorption lines are generated by neutral hydrogen. Mm-hmm. And we know that the neutral hydrogen is mostly sitting in voids and sheets, So this data basically arises from the low density regimes of the universe. And in this way, it is complementary to the galaxies that are more abundant in clusters and high density regimes. But of course, this also poses some challenges. So the fact that this data comes from the low density regimes means that we need a good description of the density field inside the voids. And that's the motivation for this paper, for this field-based approach. And also, the Lyman-alpha forest is, of course, affected by the non-Gaussianity of the cosmic web. So when we look at the large-scale structure, we see all this filamentary structure with the clusters, filaments, and voids. And all this complicated structure cannot be described with two-point statistics. So if we want to extract all the information from the data, we need to go beyond the power spectrum and the correlation function. And we need to use high-order statistics. And a natural way to mimic or to model all these statistics, all these high-order statistics, is to use a forward modeling.
Yeah. When you say that the neutral hydrogen mostly resides in like the underdense regions, this might be a naive question, but presumably not the very underdense. Like it must be the sort of intermediately dense, because the center of a void, presumably all the hydrogen's kind of left out of it. But I guess in the overdense regions, it's not neutral hydrogen anymore. It's ionized hydrogen. So it must be some sort of intermediate region, or is it really that the more underdense you go, the better?
Well, from hydrodynamical simulations, we know that it's mostly located in voids and sheets. And if you go to filaments or clusters, then it is ionized. So it would not be neutral hydrogen.
But eventually you must get so underdense that there's just no hydrogen at all.
Sure.
Oh, yeah, okay, cool. All right. Yeah, cool. So do you want to start getting into the details and
Yes. So let me just mention that I did this work together with Oliver Hahn, Jens Jasche, and Guillaume Labo. And this was done within the Aquila Consortium, which is a group of people interested in applying data science techniques to cosmology and do cosmological analysis. So I will start by giving maybe a more visual description of what is forward modeling techniques. So in these methods, we start with having some physics that determine or describe the initial conditions of the universe. And then we evolve these initial conditions using a dynamical model that encodes all the gravitational clustering and our theories for gravity. So basically, this dynamical model provides the dark matter distribution with all this filamentary structure. And now what we need is to connect this dark matter distribution with the observables, and we do this through the data model. So in the case of the Lyman-alpha forest, the observables are the flux that we observe in the quasar spectrum. So we will need to connect this dark matter distribution to the fluxes. So through this process, we generated some artificial observations that now we can compare with the real data using some likelihood, for example. And we can repeat this process for several realizations of the initial conditions or several or different physics. And by doing this, we can do inference on the density field and the initial conditions. So basically, we can tell which models and which density fields are compatible with the observations. So the advantage of using forward modeling is, first of all, that we have this dynamical model and this data model that account for all these high order statistics. So this naturally reproduce all this filamentary structure of the cosmic web. And also with this kind of techniques, we can use every single data point, and we don't need to rely on summary statistics that usually don't capture all the information on the data, and also they have complicated probability distributions that are not well known. So with this kind of methods, we can use all the data, and we can account for this complexity of the cosmic web.
And then because your model parameters includes the initial conditions, you do kind of almost get a measurement of what, not what the power spectrum was in the early universe, but the actual values of the density contrasts in various regions of the universe, which I've always thought is kind of cool from forward modeling.
Yeah, so we are sampling the density field in every voxel of our box. Yeah, so we get the amplitudes and the phases. Okay, so in the case of the Lyman-alpha forest, we are interested in recovering all this or inferring all this continuous dark matter distribution. And we want to do this from a set of one-dimensional spectra. And this means that we are dealing with an incomplete set of data. There are regions where we don't have observations, and the data is also affected by noise. Mm-hmm. So in order to do this, we will need to use statistics. And in particular, we are doing cosmology. So we have a good prior, we have the lambda CDM. We are going to use Bayesian statistics. Mm-hmm. So this means that we are interested in the posterior distribution that tells us how the density field, how likely the density field is given the data, in this case, the flux in the quasar spectrum. And this is given by the likelihood that connects the data to the density field and the prior that encodes our knowledge about the universe. So in our method, we are interested in getting the full posterior distribution. We are not producing estimates of the density field. We want to recover the full posterior distribution because we want to be able to quantify the uncertainties. So we expect that we will have a better reconstruction in some regions than others because we have better data or more data in those regions. And this is possible to quantify if we have the full posterior distribution. Yep. So the first thing we need is the likelihood. So we need a data model that describes all these absorption lines in the quasar spectrum. And this can be well described by the fluctuating and Peterson approximation that tells us that the flux that we observe in the quasar is suppressed as an exponential that depends on the optical depth and also some noise that is added to the data. Mm-hmm. So this optical depth depends on the local dark matter density field and some parameters A and beta that are related to the astrophysics of the intergalactic medium. So basically, these parameters encode what's the physical state of the neutron hydrogen that produces the absorption lines.
Okay. Do you want to maybe just sort of unpack a few of the pieces? So the little n is, I guess, just some sort of like noise, but what statistical shape is it? Just like a Poissonian shot noise type of thing, or is it a?
No, we assume that it's a Gaussian noise.
A Gaussian noise, cool. Okay, and then is there any physics? So the 1 plus z to the power of 6 probably has some physics behind it. The other stuff might just be empirical fits, but do you want to maybe unpack them a bit?
Mm-hmm. Yeah. So this is the photoionization rate, this gamma here. Okay. This temperature here is the temperature that we assume for the neutron hydrogen. Okay. And this 1 plus z would come from the density. How the density is affected by the expansion. Okay. The density of neutron hydrogen.
Yeah, I guess it's just so why the 6? I guess the density is dropping as 1 plus z cubed.
The dark matter density, yes. Mm-hmm.
And so then, is there a good physical intuition for why tau should go as the density squared?
Because of so this comes from the relation you have between the densities and the temperatures for the neutron hydrogen.
Okay. Okay. So the temperature scales as the density squared. Yeah.
Mm-hmm. Yeah.
And so this T0 is the minus 0.7 and the 2 and the 0.7. They're more or less empirical, or are they? Is there like the theory behind that? Oh, okay.
Okay. So we don't know the value of the parameters A and beta. This has not been measured from data. So in order to avoid any bias introduced by the unknown physics or the known physics of the neutron hydrogen, we are going to marginalize over these parameters, and we treat them as nuisance parameters in our analysis. So this description of the fluctuating and Peterson approximation is in real space, but of course our data is in redshift space, so we will need to also do the transformation to redshift space, and I will come to that later. So now that we have the data model, we can write down the likelihood by assuming that the noise in the data, as we said, is Gaussian. So we can write down this likelihood, and the quantities that we are sampling here are the density field and the astrophysical parameters that would enter the computation of the optical depth here. So we have talked about the data model. Now we can define the prior. So for this, we use the Borg framework that consists of a Gaussian prior for the initial conditions. So we can draw random realizations of these initial conditions, and then we evolve them using the dynamical model. So the reason why we do this, instead of just starting here from the final density field, is that we don't have any probability distribution that can capture all this complexity. We have approximations like the log normal approximation that can reproduce first and second order statistics, but we don't have a probability distribution that can capture all this filamentary structure. So what we do is to translate our problem of the inference of the density field into the inference of the initial conditions. And for this, we know that we can use Gaussian statistics.
Mm-hmm. Yeah.
So now we can use a Gaussian prior for the initial conditions, and the connection between these two fields is given by gravity. And we have a good theory for gravity that we can encode in the dynamical model.
I guess this is something that I don't think I captured properly in my intro either. That it's not just that with this nonlinear field, you can just be like, oh, well, I'm going to take the bispectrum as well and the trispectrum. That information from that primordial Gaussian stuff leaks into all of the higher order moments. You would have to measure everything. There simply isn't any summary statistic at that late stage that
right.
captures the full Gaussian thing. It's not as simple as just taking a bispectrum. Obviously, the bispectrum gives you a little bit more information, but nothing like the full initial
yes,
stuff.
Exactly.
Yeah.
So in the work framework, we have several options for the dynamical model. We can choose to use Lagrangian perturbation theory or particle mesh simulations, but these are particle-based approaches. And now with this paper, we have introduced this propagator perturbation theory. So this PPT is an alternative to particles. So when we are working with Lagrangian perturbation theory, what we have is the trajectory of fluid elements. So basically this means that we need to populate our initial conditions with particles, evolve the trajectory of these particles, and then put them back on a grid to obtain the density field. Mm-hmm. But by doing this, we're introducing some sampling noise, because most of the particles tend to cluster in the high density regimes, in the clusters and filaments, and the voids are poorly traced. Yeah. So basically, the voids are impacted by a very high sampling noise. And this is especially relevant for the Lyman-alpha forest because the data arises from this region. So we need a good description of the underdensities. And a solution to this is to use this PPT. Mm-hmm. So what you see here is the same density field obtained with both models, LPT and PPT. But with and you can see that we get the same kind of structures. Mm-hmm. But with the PPT, we got rid of the sampling noise because we don't need particles. We evolve the density field directly on the grid. But how do we do that? So this is based on the idea that we can encode all the phase information in a wave function. So we can build an initial wave function that depends on the gravitational potential of the initial conditions. Mm-hmm. And then we evolve this initial wave function using a propagator in a similar way than what we would do in quantum mechanics. Mm-hmm. So in this case, the time is encoded here in the growth factor. And this h bar is a free parameter that controls the smoothing of the density field. Mm-hmm. So once we have this evolved wave function, we can obtain the density field by just computing the norm of the wave function.
And this is something that also works in the overdense regions well, or is it doing badly in the overdense regions, but you don't mind about that because your data is mostly in the underdense regions?
No, this is doing also the overdensities well. This is actually, it would be equivalent to Seldovic approximation.
I see. Okay. So at some point it breaks down once there's been, numerous shell crossings, but until then it's still doing a good job. Okay, cool.
Right. But still, I mean, even while LPT or Seldovic approximation at shell crossing, it produces these infinite densities. Mm-hmm. And with this model, we would avoid these infinite densities, and we could see some pattern of interference. But it's also a way to detect shell crossing scales. Mm-hmm. Okay, so this description is in real space, but of course we need to do the transformation to redshift space. So this is also new in this paper. So we have added a propagator that would propagate from real to redshift coordinates. So basically it's the same idea as before, but now instead of evolving the wave function, what we are doing is to just do a coordinate transformation from real to redshift space. Okay. And basically we could convolve this wave function with the propagator and we would obtain our quantities in the redshift space.
Do you want to maybe unpack a bit of the theory there? Because defining a velocity for a wave is not necessarily a unique thing, whereas for a particle, obviously it is, and it's the velocity that is affecting the change from real to redshift space. Is there a way of understanding this thing inside the exponential? I guess you've got the growth factor there, which is somehow going to be talking about the velocities in some way or another, but
yeah. So basically, that would be the change of coordinates, right? So basically, what we do is to build an action from the change in the coordinates. Yeah.
But how? So suppose I've got a wave function at some point in space, and I want to know whether it's moving towards me or away from me. What is it about the wave function that is telling you what the Doppler shift would be?
A combination of the gradients of the wave function would give you the velocity field.
Okay. And then so this propagator is just the mathematical technique that would do what the simple Doppler effect would have done in the real world of changing the location.
Okay, so here you see a comparison between the Seldovich approximation and the PPT. In real space in the upper panels and below in redshift space. So if you compare here, you can see that we get the same kind of structures, but if we zoom in inside the voids, you can see that there is some weird structure in the case inside the voids in the Seldovich approximation. We can see some kind of grid, and these are artifacts that come from the fact that we don't have enough particles to trace the density field in these regions. And this becomes even more severe in the case of redshift space, because you see these white lines here that indicates that there are 0 particles in those regions.
I see.
And all these artifacts are gone when we use the PPT, and we get a smoother and more physical density field inside the voids. We can also see this in individual structures. So here you see a density profile for a cluster and a density profile for a void, and with both models, and you can see that we are getting the similar profiles. But in the case of the void, we get huge error bars here for the LPT, and this is again because we don't have enough particles in this region, and this problem is overcome by the PPT that provides a more reasonable error bar.
And do you estimate the error bars here by doing lots and lots of different simulations, or is it like a...
Yes.
Okay, all right.
Yeah, different realizations, and then Okay, so summarizing, what we have is 2 sampling blocks for this method, one that samples the density field, and it consists of 3 steps: sampling the initial conditions, then we we evolve the density field using the dynamical model, and then we apply the data model and redshift space. And this provides us with the density sample that now we can use to sample the astrophysical parameters, this A and beta, that enter the data model, and we iterate this in an MCMC framework. So in this method, we are sampling the density field at every voxel in our box, and this means that we are dealing with several millions of parameters. And as you can imagine, this is computationally costly. But with the PPT, we can speed up this MCMC. So basically, when we initialize a Markov chain, we initialize it in a random place in our parameter space, and these evolve towards the target regime. So usually we monitor this warm-up phase by looking at the power spectrum. So we start with a power spectrum that has a wrong amplitude, and then we see how it drifts towards the correct power spectrum. And you can see that for the LPT in this setup, it would take of the order of 300 samples. Okay, so with the PPT, we can reduce the number of samples that we need for this warm-up phase by doing a hierarchical annealing. So what we do is we start sampling at a very coarse resolution, looking only at the large scales. And when these are converged, we start opening new modes, increasing the resolution and sampling smaller scales. And we do this in several steps. So we can do this with the PPT because we have this H-bar parameter that controls the smoothness of the density field. And basically, we can select which are the scales that are relevant at each level and needs to be mapped into the next level. So when we do this annealing with the PPT, we get a faster warm-up phase, and you can see that this is reduced to more or less 150 samples. So we reduce by a factor 2 the number of samples that we need to get to the target regime. So this results in a speed up of the algorithm. So we tested this method using mock data from the Clamato survey. So basically we mimic the noise properties and the lines of sight, the density of lines of sight of the Clamato survey. And we input this mock spectra into Borg, and this provides us with a set of density fields. Each one of these density fields is a sample from the posterior distribution, and we can use them to estimate mean and variances. So here you see the initial conditions, the evolved density field, and the optical depth. And in columns, you see the true fields, the ones we use to simulate the data. Then the mean and the standard deviation estimated from the samples of the posterior. So if you compare the first two columns, you can see that we are recovering the correct structures from the ground truth.
Mm-hmm.
In particular, if you look at the initial conditions, we recover a smoother version of the initial conditions because there are several distributions of initial conditions that would end up forming the same cluster or the same filament. That's why we get this smoother version. And then if we look at the uncertainties, you can see that for the optical depth and also for the density, this uncertainty has structure that actually correlates with the mean. And this is expected for a non-linear and non-Gaussian posterior distribution. And what we are seeing here is that we get higher uncertainties in the regions where we have high optical depth or high density fields. And this is because the absorption lines in the Lyman-alpha forest saturate at high densities, and then basically they cannot transport further information, and they just set a minimum threshold of the density, but the density could be higher than that. That's why we are seeing these uncertainties. Okay. So you can see that these two fields here look similar by eye, but we can compare a correlation between, we can compute the correlation between them. So here you see the correlation between the true density field and several samples in our Markov chain for one slice in the box. So this is one slice of 1 megaparsec, and as we move in the x-axis, we would be moving across the slice. Okay. So the dashed lines indicate the position of the lines of sight in this slice, and the dotted lines indicate the position of the spectra in the neighboring slice. Okay. And you can see that we are getting a high correlation at most of the locations in this slice. But even in locations where we don't have any neighboring data, we get correlations of around 70% or above. And this indicates that the method is able to interpolate the information between lines of sight and recover all this filamentary structure of the cosmic wave. Okay, so another test that we can do is to look at the matter power spectrum. So basically we have all these density samples, and we can measure the power spectrum in these density samples. So in this method, we are not sampling the power spectrum, but the power spectrum is also not enforced on the densities. And this means that if the data requires it, the density samples can be produced with a power spectrum that is different from the prior. So it's always a good test to check that we are actually recovering the correct power spectrum, because deviations from this would indicate problems in the data model. And this is particularly challenging for the Lyman-alpha forest. So now let me illustrate what kind of physics we can do with this method. So here you see cluster mass profile from one cluster in our density field. So you see that we are recovering the correct mass profile from the ground truth, from the simulation, from the density field that we used to generate the mock data. So this indicates that this method can provide unbiased mass estimates, and it could be used as an alternative to X-ray measurements or weak lensing measurements to estimate cluster masses. Similarly to what we did for the clusters, we could do it for the voids. Here you see a velocity and a density profile for a void, and you can see that we're also recovering the ones from the ground truth. And a possible application of studying the voids in our density field would be to constrain the total mass of neutrinos, because we know that the neutrino mass impacts this or affects the size of the voids. So we could try to measure this from our density fields. We could, of course, also use this method to constrain cosmological parameters by performing an Alcott-Paczynski test. This is based on this is basically a geometrical test. So if with the correct cosmology, we expect to see isotropic structures, and with the wrong cosmological parameters, we would see elongated structures. And this has been tested in the Borg framework by Dubesh Kodiramana, also in the Aquila consortium. So he used mock data from the SDSS3, so in this case, galaxies, and apply Borg to measure the equation of state of dark energy and also the omega matter. And you can see that this method provides tighter constraints than the standard BAO analysis. So this test was done in real space. And of course, it would need to be tested in redshift space, but there are still reasons to think that the applying Borg would, to do this would provide tighter constraints than the standard BAO analysis, because given a limited volume of the survey, the BAOs have a sampling rate of 150 megaparsecs, while Borg could extract information from smaller scales.
Yeah, one of the earlier talks on this channel was by Sesh Nadatha on using voids, not using Borg. So it's probably not the absolute optimal statistics you can get from voids, but he certainly does get, because, yeah, essentially exactly what you're sort of showing there, that voids can be smaller, and therefore you can have more of them inside the same volume as the BAO, that there's complementary information there, and it does improve. But I think you're right that if you were to use a kind of forward modeling way of looking at the voids, then you might get even more information. So that's interesting. Yep.
So this was done with galaxies, but of course this could be also applied to the Lyman-alpha. So with this method, we can also obtain velocity fields. So basically we have the forward model. So we can naturally derive velocities from the forward model without increasing our parameter space. So here you see these are for the Lyman-alpha run with mock data. So here you see the one we used to generate the mock data, and here the ensemble mean. So we are getting velocity fields at high redshift, where this kind of information is usually hard to obtain otherwise. Mm-hmm. And we could use these velocities to combine them with the density field in order to study the matter flow. So with Borg, we are obtaining densities and velocities that are consistent by construction, because they are derived from the same forward model. And they are both constrained by the data. So we could use this to study structure formation and test structure formation model. Mm-hmm. So summarizing, the analysis of the high redshift universe in 3 dimensions is possible from the Lyman-alpha forest. In this method, we constrain the dark matter distribution and also the astrophysical parameters that are related to the physical state of the neutron hydrogen. And this makes the analysis more robust against any systematics introduced by the unknown physics of the neutron hydrogen. And here we have improved this method by including this PPT, which is this field-based approach to provide a better description of the underdensities. And also in a more technical side, it helps us to speed up the algorithm and reduce the computational cost, particularly of the warm-up phase. And finally, with the data products of Borg, which are basically the dark matter distribution and the velocity fields, we could do cosmology or test structure formation models.
Yeah. So you have you applied the actual stuff you just described with the Lyman-alpha forest and PPT and things to actual data, and you have constraints on omega matter and things, or is that what's coming next? Or
that's coming next.
Oh yeah, yes. Okay. Which is normally the next question of where to next. So I guess I'm already preempting that. Yeah, what comes next? I guess a few things have been maybe already brought up. There's applying the stuff you talked about to data, and then also maybe this Alcock-Paczynski with voids and adding redshift space distortions. But feel free to go into both of those things in more detail if you want to, or what else is coming next.
Yeah. So for this method, the first step would be to apply it to a more realistic data, like data coming from hydrodynamical simulations and including all the baryonic effects, and then of course applying it to real data and try to constrain cosmological parameters or the neutrino mass.
And there's do you have, I don't know, observer colleagues and collaborators? Is this in the pipeline, or is this more futuristic than in the next sort of 6 months or 12 months?
No, the hydrodynamical simulation is in the pipeline.
Oh yeah, cool. Okay. Yeah. And anything else that's coming up, or is that all you want to mention?
Well, for in a more general way, maybe that as we should start analyzing the data, also current data, also galaxies and so on, for using high order statistics to go beyond this power spectrum and correlation functions to try to extract all the information from the data.
Yeah, cool. All right. Outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
Yeah. So of course, as everybody, I'm very interested in the H-naught tension.
Yeah. Yeah.
And to see whether this comes from, or whether it's systematics or something else. And more in long term, I also think it's very exciting, all this gravitational wave field. So, and what kind of physics we will be able to learn from this data when we have more detections and we can do cosmology with it.
Yeah. Obviously, one of the things that they can do is also measure H-naught as they get more of them. Cool. Well, thank you everyone for watching. If you like this, don't forget to subscribe and click the bell if you want to be notified, and share the channel with your colleagues. If you have any questions or suggestions, leave a comment. I'll make sure Natalia sees them. While you're here, you can watch another video. This video by Sesh about voids is probably the most relevant one to this talk. And thanks again, Natalia, for the great talk.
Thanks.